Hello, everybody. Welcome to the next session of the PML reading group. This week, we're going to be covering Chapter 10, Logistic Regression, and Antareep will be once again presenting the material. So let's get started.
Hi Perry, thank you, thanks a lot for the introduction. Hi, hello everybody. So let's begin. Let me share my screen. Right. So today's topic is my pen, mouse pointless pen. So today's topic is logistic regression, something you must have heard about. And if you have studied linear regression, so logistic regression comes along with it. So what exactly is logistic regression? So in linear regression, what did you do? Let's say you are to predict temperature. So there are multiple parameters, parameter 1, parameter 2, parameter 3, parameter 4. And based on these four parameters, you predict the temperature of the day, what the temperature would be. It might be 10 degrees Celsius, it might be 30 degrees Celsius, it might be 45 degrees Celsius, it might be -5 degrees Celsius. Now I set a threshold of 25 degrees Celsius. I don't want such specific details. No, I don't want such specific details. I just care about, just let me know what is the temperature. Is it high? Is it hot? Or is it cold? And what would be the parameters? So how do you decide something is hot or something is cold? It is relative. It is a relative parameter. So you decide a threshold. So that threshold is 25 degrees Celsius. For instance, let's say you're doing an experiment and you decide a threshold to be 25 degrees Celsius. Anything above it is considered to be hot. Anything below it would be considered as cold. So what would be cold? This is cold. This is cold. This is hot. This is hot. What did we do? Just a moment before, we were taking parameter 1, 2, 3, 4 and predicting a numerical outcome, or we were doing linear regression. If you apply, if you go a bit ahead of linear regression and add a classification factor to it, that is logistic regression. So welcome to logistic regression. If you've understood this particular concept, you've understood logistic regression. You should be very comfortable with it. Now, let's remove this. So different there are multiple names of logistic regression. They are also known as logits, maximum entropy. This is a very popular debate on internet, but my my take on this is it is a classifier, and that is what it is. Two class or multi-class. Ideally, theoretically, it is two class. What sklearn provides is multi-class also called a sigmoid function. A very brief overview. So this is, let's say this is something we just discussed. This was your linear regression line. And what we do is decide a threshold. Any value lying um, in this region would be made to fall down here, down here. Or anything above here, the threshold would be made to, will be made up, will make a projection of it on the y equal to 1 or y equal to 0, whatever the threshold is. So that is what logistic regression is. This is what logistic regression is. We will talk about this as uh, shape or those kind of things, but this is a very brief introduction of logistic regression. So turning linear regression into logistic regression, that is the very superficial idea. Now, what did we do in linear regression? If you recollect, we discussed about ordinary least squares. That is what linear regression is or does. But what we are about to do is maximum likelihood estimation. What exactly is maximum likelihood estimation? It is a method which helps you to estimate the parameters. And what is exactly it is? It's like a mathematical concept where the where you're trying to estimate the distribution from which the parameters have might have come. So let's say this is one distribution, so the parameters must have come from this distribution. So this is what exactly maximum likelihood estimation does. Why not ordinary least squares? Why maximum likelihood estimation? We'll talk about it. But this is what, on a very superficial level, maximum likelihood estimation does. Joint probability mass function set of parameters can be used in a normal distribution. Based on maximum likelihood estimation, the cost function of linear regression was very simple, just the predicted value minus value minus the real value minus the predicted value whole square, and that was the cost function of linear regression. But what about the maximum? What about logistic regression? We don't use that. Why maximum likelihood estimation? Because that particular ideology, y minus y cap, leads to, so this is linear regression, right? That was linear regression. The line is linear, so if line is linear, it will always be differentiable. But we are talking about single class, multi-class, binary class, multi-class classification. The curve might be very zigzag, so there are possibilities that you might be stuck up in a local optima. If this is not getting to you, don't get worried. If you are able to understand, please follow along. If you're not, nothing to worry about. So let's say you are stuck up in a local optima. There are very high possibilities that it might happen if we take the similar route as we have taken in the linear regression. So what we do is use maximum likelihood estimation. Maximum likelihood estimation is a different approach. We won't get into the mathematics, but on a very superficial, this is why we use maximum likelihood estimation. Advantages of logistic regression: does not require high computational power, easy to implement, interpret, does not require scaling of features, provides probability score of observations. Disadvantages: if there are large number of categorical features, very difficult, vulnerable to overfitting, and if independent variable has low correlation. So how to remember these majority things you should remember is disadvantages, because these are the cases you should have in mind, that if your use case is matching with the disadvantages, then you should not use logistic regression. So if the independent variable, if your independent variable has very low correlation with the target variable, maybe logistic regression is not a good choice to proceed with. Try SVM, try XGBoost, try random forest classifier, but not logistic regression, right? If you have a large number of categorical features within one variable, so let's say you have ethnicity, there might be multiple types of ethnicity, so it's not preferred to use logistic regression, right? So kind of, but let's say these are not the cases and you have features uh, which scaling might be needed. But how about taking up logistic regression? It does not require scaling. Yes, if you do scaling, it is always beneficial and it improves the performance, but it's not mandatory. Like if you have to deal with KNN, scaling is must. So maths of logistic regression, let's begin. So this is something you would always observe if we talk about logistic regression. What is this P? P is something we call as odds ratio. So P is something we call as odds ratio, and you must have seen this as well. This is our good old friend sigmoid. What is sigmoid? 1 by 1 plus e to the power minus x. The very starting point of deep learning. So if you are deep learning, so I'll be taking up deep learning with images. Then also I'll be discussing sigmoid. Uh, but this is the very starting point of sigmoid or those kind of things. So now we have this logistic function. This is this, and yep. So let's try to understand how do we get to the desired output. So here P is not the probability, but rather we describe P as the odds ratio, or rather to obtain the formula, we describe it as log of odds ratio. And if you do log of odds ratio, what it would be at the base E. So it is P by 1 minus P equal to e to the power beta, removing the log. If I remove the log, so it would be beta plus beta 1x. After solving, you get P equal to e to the power beta naught plus beta 1x divided by 1 plus e to the power beta naught plus beta 1 x. Simple mathematics, just the assumption. So you have y equal to b naught plus b1x, right, in linear regression. This is something we all agree. But what, y is anything, right? Y can be anything. It can be z, it can be q, it can be r. But let's say I don't name, I assume that the y, whatever the y is my log of odds ratio. What is log, what is odds ratio? Just ignore it for a while, but just remember the word. It is log of odds ratio. Logarithm of odds ratio. What is odds ratio? What is logarithm? Just throw it out of mind. Whatever it is, logarithm of odds ratio is log of p by 1 minus p, and equals to our good old friend of linear regression. And thereby we get to the formula of logistic regression. If you divide by if you divide it by e to the power beta naught plus beta 1x in the numerator and denominator, you get the formula of 1 by 1 plus e to the power minus beta naught plus beta 1x, which is a sigmoidal function. So let's proceed to the next slide. The next factor is understanding the cost function. This is pretty much asked in interviews or anything. You might be asked about cost function, which is log loss, logarithmic loss. And the reason why we use log loss and not the one which we saw in linear regression, the one which we saw in linear regression was this one. So we saw in linear regression simple h theta I minus yi whole square half. So this is not what we are using. This is pretty different, but ideally we should have used that only. No, we are dealing with probabilities this time. And if you're dealing with probabilities, you assume the distribution to have come with maximum likelihood estimation. Although we could have transformed the I mean, this might be sounding very counterintuitive. Like at one point I'm saying that yes, linear regression line, just transform it to logistic regression. Then why not just take the estimated probability? Let's say the probability would have been 0.8, but I said the probability is 0.6. I can just take the difference and square it up and those kind of things. No, that is you can't take the difference of probabilities and square it up. That doesn't make any sense, right? So that's why you need to deal it with in a different manner. That this works if you have, let's say, estimated price is 800 and predicted price, real price is 800, predicted price is 600. Then you take the difference, square it up, and take the average of all such errors. But we are not dealing with, we are dealing with the errors of probabilities. How do you deal with errors of probabilities? First, you need to have a mechanism to deal with errors of probabilities. And the it's not maximum likelihood and then cost function. It is like more of cost function than maximum likelihood estimation. So this is the cost function. Don't get into the derivation, just remember it. If you have time, if you have the energy, just try to Google and search about cost function or the cost estimation. Log loss, you get a lot of stuff, lot of stuff. But this is what it is. So you have yi is the predicted and then log of yi, and take the 1 minus. So it's p, or another common form, p log p, and plus 1 minus p log 1 minus p. Good enough? And all the points, summation of all the points from 1 to n, and average it out by dividing by n. This is the log function. Now this is also a way we had discussed cost function versus error. Cost function versus error. This is the plot we discussed, and this is something we did spend our time on. But something which might be asked is, what if y equal to 1 and what if y equal to 0? So what if y equal to 1? Let's substitute y equal to 1. So this whole parameter gets zeroed up, and you have all the y log y parameters. So if you have y log y parameters, uh, this is pretty much it. You can just plot out all the values for x equal to 0. Um, for h theta approaching 0, the cost would be negative. So if it is log of 0 is usually an infinite number, so it's basically negative, those kind of things. And if the other way around, if y equal to 0, you have this term as removed. You have 1 minus y log of 1 minus y. So if h theta is approaching 1, if h theta is approaching 1, then you have, if h this to make this approach infinity, how can this approach infinity? What's the curve of log? This is logarithmic curve, right? This is the logarithmic curve. How does log approach infinity? When it is approaching 0. Um, so this is the curve of logarithm. This is the curve of logarithm. What is log? When does log reach value of 0? Let's say we are taking at the base 1. Log 1 is always 0, and log 0 is infinity, minus infinity. And anything above log 1 is positive. So this is the curve of log. If I want to make it reach infinity, I need to have the value of log. Then anything the functional value of log as 0. So if y equal to 0, then we have a different kind of curve. And if y equal to 1, we have a different kind of curve. Those are these two curves. If I hope this is clear. If not, don't worry about it. Just uh, fiddle with the values and you will be better off with it. So again, a bit of mathematics, but now I won't be solving up. I'll have the snippets in front of you, which are pretty much solved. And so we'll be discussing what's next. We'll be discussing how to obtain the predictions, different kind of predictions, and what do they mean and signify. Plus, we'll be discussing about how to understand the confusion matrices and these three parameters, which are pretty much used. Sigmoid function is something we already discussed, but always remember this thing. This is usually asked in questions and competitions for sigmoid, for tanh, and there's one more activation function which I don't remember, but these are pretty much usually asked. And then you have understanding the slopes. We'll discuss about the logistic regression and the solver methods. Then we finally wrap up with regularization. So this is the next 40 minutes. We are pretty much on schedule. So let's begin. Oh, so obtaining predictions in logistic regression, obtaining predictions, how do you obtain predictions? And so this is something we discussed, that this is log of odds, the entire linear regression thing. So and this is hereby we obtain the calculations. I just solved this in front of you. No need to worry about it. So what is logit? Logit function is log of odds ratio. That is logit, a short name, logit. Log of, just remove the ink, ln of pi by 1 minus pi. Now what is pi by 1 minus pi? This is known as odds ratio. What is odds ratio? We'll discuss. Now there are two types of curves. We have discussed about this. This is your S-shaped curve. For this happens for linear functions. If there's a polynomial function, then you have bell-shaped curve, where we have x, we have pi, and it happens like this. So this is what it is. Yeah, let's discuss odds ratio. What is odds ratio? It's a very mathematical term, odds ratio. Usually discussed in terms of, let's say you have a probability value of 0.3, 0.7 of getting the deal. So I would ask you what are the odds in favor or odds in uh, those. So usually first we start with odds ratio, and odds ratio is the ratio of success, which is 0.7, upon ratio of failure, which is 0.3. Now success can be anything. Success can be failure as well. Don't get by this term. Just success is the thing which you are concerned with. It might be a negative thing as well. So let's say success of uh, success of um, going down. Let's say success might be the stock price going down of any XYZ stock. So that is not a success, but that is something the matter of concern. So that is a better word. Probability of success is something which we are concerned about, or something which whose probability value we are dealing with. So that is how the odds ratio is calculated. And this is what we call as odds ratio. If you want to know about the probabilities would have been obtained once we had solved this equation of log of odds ratio equals to beta 1 plus beta naught plus beta 1x. If you had solved this equation in terms of p, you would have obtained probabilities. Now let's see what we do exactly. If there's a threshold of 0.5, if there's a threshold of 0.5, you draw an imaginary line. Anything which is greater than or equal to 0.5 will be projected upwards and thereby will be termed as label 1. Anything below it would be projected below, and once you project it below, it would be labeled as 0. Good enough. And then we have this S curve where we say that the Y values lie within the range of 0 to 1. Something which this pretty much explains. Odds ratio and log odds ratio, I think this must be clear by now. This is the odds ratio, this is the log of ratio, this is the probability value. Now, once you have obtained your classification results, so these are the things you would be dealing with stats models, not a scalar. No, 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 no. These are something you will be dealing in stats models. So if you have time and if you've understood the theory well, you can start experimenting with stats model, but I wouldn't suggest directly jumping into stats model. If you have a good understanding and hold of Skillon's logistic regression, then it's a good way to go. It's stats model. And yeah, these kind of things are usually generated there. So let me share something. Let's say I'll show the ordinary least square methods. No, the logic method of stats model which generates such kind of reports, and that would be pretty interesting. Any questions still here? We are going to proceed to the next half of the discussion. Any questions? Oh, in the multi-class case, why we build multiple binary, we build multiple. Yes, it is one versus many case, right? Sorry, didn't get it. Why we divide by 1 minus p? It is just the formula, Lucy, and it's like the log of odds ratio is p is success, 1 minus p is failure, and log of odds is something odds ratio is a standard mathematical definition. And for logistic regression, we try to find log of odds ratio, log its probability of success. Yes. So I'm assuming that everyone is following along and we can proceed. So next part of the lecture is a bit more about understanding what the results are. So let me keep this open here and this here. If I click F5 now. Yeah, pretty good. I'll be able to get your messages. So this is something you must have seen and you will be definitely asked about interpreting these kind of things. So there are 4 combinations. So it is made by classical confusion matrix. 2 by 2 is pretty simple, but let's discuss 3 by 3. Let's discuss 3 by 3. So the best way to remember this? The way I remember this. So the best way to remember this is the way I remember this. And this is true combination of true, false and positive, negative. So if you combine true with positive and if you combine false with positive. So first you need to understand what is positive, negative, and then you need to understand that it is whether or not it's true or not. Positive, this part of the prediction, this part is what I call as. So this is nowhere. Please listen very carefully. If you listen, you will always remember for rest of your life. I have never ever forgotten this thing because this was pretty good. This part is for outcome predicted by the model, and this part is for the adjective. It describes whether or not the outcome predicted by the model is true or false. You get it? So what would be true positive? Model predicted read it from right and go to left. The model predicted it positive, but it was actually positive. So what does false positive mean? Model predicted it positive and it was not positive. It was not positive. So goes for negative. Model predicted it negative and it was actually negative. And for false negative, it is model predicted it negative and it was not negative. This happens not in general, but for a class. So for every class, for each class, let's not write with mouse till I get a good writing pad. Yeah, but it's comprehensible. Yeah, so I mean, for Apple, you'll have a different value for true positive, true negative, false positive, false negative. So is the case for orange, so is the case for mango. So now let's solve it together, right? If time permits, how much time is left? We have, I mean, let's take it. Let's get it done. This was not actually logistic regression. This is me talking about evaluation metrics. There's a playlist of mine on my YouTube channel that is metrics evaluation. I have discussed all the metrics in very detailed manner. If you have time and energy and devote some time to it, you will have a greater understanding and good depth of it. So let's talk about Apple. Now, Apple's true positive would be I predicted it Apple and it was actually Apple. So search samples for Apple, not for everybody, is 7. True negative for Apple would be I predicted it not Apple and those were also not actually Apple. So this lot, this lot is true negative for Apple. I predicted Apple, but it was actually orange and mango. So I was predicting it. Is it positive or negative? Doesn't matter. Anything which is under concern is positive, right? Anything which is not under concern is negative. I just told you a moment ago in log-outs ratio, right? If you remember. So anything which is under concern is positive. Under concern at this moment is Apple. Apple is neither positive nor negative, but it is under concern. That is why I would consider it positive. So I predicted it positive. I predicted it Apple, but it was not actually Apple. So those samples are these. What are these? Predicted positive, but were not positive. So false positive. Of whom? Of Apple. Well, I predicted it not Apple or negative. However, however, these were actually apples. So I made a false negative. Any confusion in this? Any confusion in this? No? Let's move on. So assuming that you have a good clarity and have the ability to calculate true positive, false, true negative, false positive, false negative, you will be asked, you will be more concerned with calculating accuracy, sensitivity, specificity. But what you would be more interested in knowing the essence of it, because that is nowhere discussed, and I am discussing the everything you have must have observed that I usually take up the things which are not discussed, because things which have discussed are easily available are something you must be already knowing. So what is accuracy, what is sensitivity, and what is specificity? is more of a concern to me. But yes, you must remember the formulas for your exam point of view, interview point of view, anything. But when to use it? It means the number of correct identifications for each class. So you have true positives by true negative for each class. If you have three classes, apple, banana, orange, apple, mango, orange, you need to calculate the true positives and true negatives. So it is accuracy for apple. Then you have to, let's say you have to calculate overall accuracy. How do you calculate overall accuracy? You calculate accuracy for apple, accuracy for mango, accuracy for orange, then you average it out. But let's say accuracy of apple would be true positives of apple plus true negatives of apple by true positive of apple plus false positive of apple plus true negative of apple plus false negative of apple. This is what accuracy is mathematically. But what does it mean? It means that you need to take the true positives of you need to take the true positive values of apples, the ones which were actually apples and predicted as apples, and the ones which were not apples and were predicted as apples, and that is what we call as accuracy. Where does it fail? Let's say there's a highly imbalanced data set where 99% of the data set is you are detecting whether or not customer would click on a link, or you're predicting whether or not there's a chance of fraud. So 99% of the chances are that customer would not click on the ads which are being showed, or 99% of the chances are that there would not be any fraud case. So if you just simply make a Python code which does if return false, that would be a 99% scoring model, but that is not what we are looking for. We are more concerned at 1%. So those are not the good cases where you should be using accuracy. Accuracy should be used where the data set is perfectly or nearly perfectly balanced. Now, let's discuss about sensitivity. What is sensitivity? Used to quantify the correctly identified positives. Yes, right, Mike. Absolutely right. So is used to quantify the, basically just get to the formula. You have true positives. What does true positive mean? True positive means that um, the correct, the predictions which were made, let's say we predicted apple and it was actually apple, divided by we predicted apple were actually predicted apple, and we predicted it as not apple, and the prediction was not correct, which means those were also apple, or those are something we were concerned of. So let's say I'm more concerned of apples, or I'm more concerned of fraud cases, then I would be more interested in talking about sensitivity. Getting my point? Now specificity talks about the other way around. It talks about the negative cases. So let's say not apple, the cases which were not apple and were actually correct predictions, I say them as true negative. So is the case with false positives, I call them as apple but were not actually apple, so they were also not apples. The amount of not apples predicted correctly or identified correctly is specificity, and that's it. Sigmoid function we already discussed. Comparing the slopes. So this is your standard good old friend 1 by 1 plus e to the power minus x. Then you have, if you double the slope, it becomes steeper. If you add a constant, it shifts right. If you add plus, a simple mathematical concept, plus means right to the origin, minus means left to the origin. Good enough. Now we are here for the SQL and logistic regression. We'll discuss it in a while, and then we have regularization, and we'll wrap up the session. Yep, we are running good. Just a sec. So let's open this particular thing, SQL and logistic regression. Logistic regression. I think now we are well prepared to talk about logistic regression. So these are a bunch of default parameters you should be knowing, and let's talk about the documentation and what it has to offer. There are also these kind of things you must check it out. The examples using logistic regression, these are pretty much good examples of logistic regression where they talk about how to use logistic regression, plotting logistic regression. Sometimes you might be interesting. So I'm not able to discuss a lot of things, but this is pretty much, I mean, Escalon's examples are very badly organized, but if somebody takes the pain to organize this, it's a very good tutorial point. I mean, a very good starter point if you have the energy to go through each and every notebook. Lot of information is being provided at a single place. All right, now we have this. What are the default terms? We have penalty as L2. We have dual as false. To toll equal to 0.001. C equal to 1. Doesn't make any sense. Let's read the description. So logistic regression logic max int. If you have watched my slides very carefully, this particular line, the first slide was stolen from here or taken from here. So this is the slide number 1, which was the opening slide. This one, this particular line is taken from here. Now in multi-class cases, which it handles automatically, the Escalon's logistic regression, it handles automatically the multi-class cases. The idea for this is one versus rest thing, which is done by, as mentioned by Mr. Perry. This is how it is done. One versus rest scheme. So the multi-class option is sent to OVR um, and uses the cross entropy laws if the multi-class option is sent to. What is cross entropy is what is what is this binary cross entropy laws, there's multi-class cross entropy laws. This is something which I'll discuss in much more detail in neural networks for images. I think that is a better place to discuss this. Then we have this class implements regularized logistic regression using the liblinear library, Newton, CG, SAG, Saga, LB, FGS solvers. Note that the regularization is applied by default. It can handle both dense and sparse input. The C ordered arrays or CSR matrices containing 64 bits for optimal performance and those kind of things. Neither did I understand it very well. So let it be. The Newton CG SAG LG solvers. We'll discuss about solvers. Support only L2 regularization with primal formulation and no regularization. The libneeded solver supports both regularization. So it's talking about if you select solver, what kind of regularization you can adopt to. And we have a good summary table for this, which I got from internet. And yeah, let's discuss the parameters. What is penalty? So we have not discussed this. Let's discuss this. Sorry, didn't I? I remember precision recall F1, recall and sensitivity are the same, but I'm not sure how other is later. Yes, recall and sensitivity are same, but not in the case of specificity. These are different terms which are used. There are multiple terms. We have F1 score, we have recall, we have sensitivity, we have specificity, we have precision, and then we have so there are F1 beta, there's there's balanced accuracy score, there's multiple metrics. So it ultimately boils down to what we are concerned about, and these are just a bunch of. I just wanted to explain the way to interpret how what these particular metrics are about. So let's first talk about this regularization. So regularization shifts your model towards the bias side of the things. So what is regularization? If anytime you find your model to be overfitting, your natural instinct would be to perform regularization. And regularization makes for a more generalizable model. How does it does? So if your model is overfitting, that means it has high variance. If your model is underfitting, it has low bias. It has low bias, or it has high low variance or high bias. Do you understand bias versus variance? If not, check out my YouTube channel. There's a playlist, metrics evaluation, bias versus variance, pretty much explained. Now L1 regularization adds, these are how do you penalize, or how do you increase the how if it is learning every data point. So what is overfitting? Let's say F1 is the harmonic mean of the, yes, what is it? What is harmonic mean? Harmonic mean is um pretty much that 2 by 1, 1 by f, 1 by precision, 1 by recall. That is pretty much harmonic mean. 2 divided by 1 by x plus 1 by y. So what is average? Average is x plus y by 2. Geometric mean is x into y raised to the power 1 by 2, and harmonic mean is 2 divided by 1 by x plus 1 by y. So this is what is harmonic mean. Now replace x with precision, y with recall. It would be 2 pr by 1 plus 2 pr by p plus r. This is what F1 score is. So it is basically harmonic mean. Why harmonic mean of precision recall? Because precision and recall are pretty much against each other. So you might have very high precision, but it's not possible to have simultaneously a very high recall. If you are concerned about both the values, you should use F1. If you are very much concerned with the precision, what is precision? True positive by true positive by false positive. If you're concerned with the true positive identification of the uh, this is a very different, we are going off topic. Just refer to my playlist. We just 15 minutes left. Refer to my playlist. We are getting off topic. Pretty much explained over there. This is regularization shifts your model. So what are we talking about? We're talking about regularization. Regularization is something which tries to remove the overfitting. How do you remove the overfitting? You have a model, and model is trying to plot its fit itself to every and each other point. What do? You just ask it not to fit to each other point, and just make a simple go through it. If that is what it is, then we had talk about regularization. And yes, so this is what it is. So we are trying to add a penalty or penalize the regularization. If penalty is to be added, and that is degree 1 penalty, we call it as L1 regularization. If degree 2, we have L2 regularization. Usually L2 works better for logistic regression. In-depth video, just I can share, but pretty much on a very superficial level, this is what it is. L1 does with some feature selections. L1 does, I think it does with dropping of some features. I don't exactly remember. Just check it out. One does drops of features. One does reduces the values of features. Then we have solvers. So this is solver. We have multiple solver options. So I'll be discussing, this is the particular call line of the class method, logistic regression. You have penalty parameter, you have dual, you have toll, you have C, you have fit intercept, you have intercept scaling, class weight, random state, solver, max iterations, multi-class, verbose, form start, and jobs L1 ratio. Multiple parameters. I will be discussing the ones you should be supplied with at this moment, at this point, and the ones which are usually mostly dealt with. So what is solver? Solver is the one which does the solving, and there are four kind of solvers. So one is Newton CG method, classical Newton method, not good for large data sets. This is the default solver, LBFGS, or the very full form is limited memory, Broyden, Fletcher, Goldfarb, Shano solver. Approximate using the second derivative matrices. I don't know what it does exactly. This is on a very superficial level. If you are asked somewhere, or you must know on a very superficial level, linear is a very popular alternative for LBFGS. Linear does for very large data set classification, and coordinate descent algorithm. Coordinate descent is based on minimizing a variation function. Then you have SAG and SAGA. SAG is stochastic, uh, stochastic gradient descent, some those kind of things. And this is a summary of it. So if you have labeling here, it won't be doing this one versus, it would have one versus rest. I think everybody has one versus rest L2 penalty. So is everybody has, not everybody has one versus rest. L1 penalty is only supported by linear versus Saga. And faster for large data set is SAG and Saga. And then you have robust to unscaled is first three ones, and then you have penalized the intercept, which is a bad thing, is done by linear. Elastic net is something which we call as L1 plus L2 penalty, both combined, and that is done by Saga. So these are multiple options. These are, if you're trying to hyper tune the parameters, these are those. Now let's discuss the parameters. You have multi-class, you have multiple options. Either you can go from one versus rest, or you can talk about multi-normal. What these are, you can search about it. Warm start is one thing. L1 ratio is there if you are choosing the penalty as elastic net, or something which is a combination of L1 penalty and L2 penalty. Max iteration is the number of, since we are doing gradient descent, we are not using the statistical methods. We are doing a gradient descent, and we are trying to estimate the parameters using the gradient descent. Number of iterations you want. Solver, we have discussed solver. Random state is used to have a reproducible result. Let's say you did and trained the model for one set of data at a random state of 2022. So anybody with the same parameters, values, and the same data set, having set the random state as 2022, will always and always receive this same output values of the accuracy and those kind of scores. Now we have C. C is an important factor. C is the smaller the value of regularization. Small values means a large regularization. So if it is basically inverse of regularization strength, or how much regularization you want to add. So initially we have 1, but you can decrease it to 0.1, 0.5, and it would have a greater regularization, or greater penalization, or less overfitting. In case your model is overfitting, then only decrease the regularization. If your model is overfitting, then decrease the C value. If not, don't mess around with the C value. And these are big things. Penalty we discussed, L1 penalty, L2 penalty. Can we apply statistical MLE? I think we can apply. I don't exactly know, but it is majorly the thing which stats models does. Logic in stats models, but I'm not sure about sklearn, because MLE is something which is implemented behind the scenes by Logistic Regression, this thing, but how can we implement? I don't know. I've not actually done with that experiment with it. And yeah, pretty much it. Thank you. That's it. That wraps up today's session. I was actually planning to discuss code, but then I realized discussing code would let me cut and shorten up the theory part, and that is something I didn't want to happen. So let's let it be. I'll share with Mr. Perry the GitHub repo which I plan to make for both these sessions. And I'll share the GitHub repo with datasets you can experiment out with the Jupyter notebook or those kind of things. Any questions? Let's have questions. Just open your mouth, open your mic, and just jump in.
Yes, feel free to unmute everybody, and now's a good time to ask questions. So I had a question about the multi-class case. The way I remember it is that you actually end up building a number of different binary classifiers to handle multi-classes.
Yes. It is usually 1 versus s number of binary classifiers to deal with multi-class.
Okay, I imagine sklearn hides that aspect of it for you.
Sorry, what is it?
So when I studied logistic regression, I remember in the multi-class case, we were told that you have to train a number of different binary classifiers.
Yes, in theory, just what I discussed is it. In theory, we always have a bunch of multiple binary classifiers which are based on, like, theoretically, it's always 0 versus 1.
Right.
But in the sklearn, they tried to implement it for us for multi-class classification as well. So in sklearn, it works as everything which is not the class. So we have apple, mango, orange. Apple is class 1 and everything is class 0. Now same will happen for mango, same will happen for orange. So this
Right.
is something on a very superficial level I know about dealing of multi-class classification for by the logistic regression.
Right.
Yeah, ordinary least square method is something we just discussed, that ordinary least square method is a method which is good for predicting a linear method. Like, what was ordinary least square methods? We were taking the difference of the predicted versus the real, and then derivate making the derivative of it with the respect of the parameters, right? That was ordinary least square methods. So that has an one underlying assumption that the curve is linear. Now we don't have a linear curve over here. It is not a linear curve. So if you don't have a linear curve, what might actually happen is there might be multiple such it will be a convex curve where there might be multiple minimas. If there are multiple minimas, what might happen is it might stuck into a local minima. If it gets stuck into a local minima and those kind of things happen, so and curve is not predicted using these kind of things, ordinary least square methods. So the better method out is to use maximum likelihood estimation, which tries to estimate where the data distribution might have come from. Ordinary least square methods, at least from my own understanding, we cannot solve using ordinary least square method. Reason being that or OLS is used is based on the fundamentally based on the assumption that the curve is linear and is not even differentiable, is a linear line, and for a linear line OLS is there. It's a non-linear curve, might get stuck into a local minima. If you don't want to get stuck into a local minima, the best way out is use maximum likelihood estimation. OLX can give negative probability values. OLS can OLS is a method to find the parameters as per my understanding. So it's nothing with probabilities and those kind of things. So we're just trying to estimate the parameters, and parameter estimation is done by OLS or MLE. Once you have the parameters, then you can make the predictions using the parameters. No, it is the S kind of line. The S is not linear, it's an exponential thing. It's not a linear thing which separates the class. In logistic regression, we discussed a sigmoid kind of thing, the S-shaped curve. That is what separates the classes. The linear line is something which I asked you to remember as thresholding, the one which was passing from the midpoint. This was the linear line, whereas a virtual imaginary line. You can set the threshold very higher, you can set the threshold very lower. So if you set the threshold very lower, the projections would be limited. Why can't we can't solve analytically logistic regression? Yes, we can't solve analytically the logistic regression. It is usually an iterative approach based on gradient descent. Gradient descent we discussed. The reason being very much similar to, can we use gradient descent to optimize? Yes, gradient descent is used to optimize. That is why we have a parameter as maximum iterations. So for how many iterations do you want the gradient descent to run? MLE versus gradient descent is something. MLE is the gradient descent is used to estimate the parameters and go get along with it. So gradient descent was also there in linear regression. So it's one of the methods. So gradient descent is an iterative method which tries to predict the parameters based on the values of the prediction. So if you have predictions, how far is from the ideal prediction of the cost versus error curve, get the gradients of it, then update the parameters. That is what gradient descent does. Yes, sure, get to the email. You have my contacts. I think you must be having. Did I share anywhere? No, I did not share. So reach out to my email.
You can also ask questions in the deep learning group and tag.
Yeah, I'm also available there. I am usually available there. And email is fine. You can ask by email. You can, if you can want to directly contact on LinkedIn, you can contact on LinkedIn. What else? Any other social media that you prefer is fb.com/Android channel. Apart from it, pretty much this.
And the slides will be made available as well as the video.
Yeah. What is it?
The slides in the video will be made available, and I'll post that to the deep learning group. It's also, the links are also in the distribution emails I send out every week.
Yeah.
And feel free to contact me as well if you are unable to reach Enter Reap or any of the other presenters for that matter.
Yeah, I really wanted to share the code and do some live coding with you, but there's a hard crunch of time on me as well as on you guys. I mean, it doesn't seem nice to unnecessarily extend the session. So let's
yeah, no, that's fine.
Yeah. All right.
Okay. Does anybody else have any questions?
You can use analytical methods. You can definitely use analytical methods, but the results are not guaranteed to reach a good. I mean, it might be that you might get stuck into a local optima. That is what is the prime concern. You can definitely use the ones that we used, OLS. OLS can be used. However, you might get stuck into a local optima. That is what I'm trying to say. You can use this method, although it does not have a closed form solution. Closed form solution, or better to say, is like there are chances that you might get stuck into a local optima. So that is something we are trying to avoid. The best way to do that is using a different approach, and that approach is maximum likelihood estimation. How that works, that's a very different ideology or concept. We can discuss that, and you add me to the group email address. This one is for Mr. Perry. So the maximum likelihood estimator is a different process. We can discuss that. If you want, we can discuss that in the next session, as that would be my last session. So we can definitely extend upon that. But very superficially, ordinary least squares can be used for logistic regression. Do not use the statement anywhere in the interview. Ordinary least squares, the reason I'm avoiding this statement is valid. Ordinary least squares can be used in logistic regression. The only thing is you'll have a very bad logistic model because it would be stuck somewhere in the local optima. To avoid that, we use anyone. I usually used to share. So I'll get back to it. So you have ordinary least square. So the reason is you can use that, but it's very possible that you might get stuck to a local optima, and that is something you must avoid. And that is avoided by use of maximum likelihood estimator. How maximum likelihood estimator works with the help of gradient descent. Gradient descent I already explained. What is maximum likelihood estimation is something I did not explain, and that is what causing the confusion. Don't get into it. I'll discuss maximum likelihood estimation in my session of neural network for images. If time permits, I'll discuss. Else, don't unnecessarily get into it. Just understand what maximum likelihood estimation on a very superficial level is. You have a bunch of data points, and so what neural network for images is. Neural network for images is we are trying neural network for images is not trying to understand image, it is trying to understand the data. So that is also kind of maximum likelihood estimation, but not exactly. But we do use gradient descent, and anywhere we use gradient descent is the place where we are trying to understand the underlying data distribution. If you're trying to understand the underlying data distribution, you're just trying to understand what the data distribution is. And so is this case, we're trying to understand the underlying data distribution, and this particular by experiment. So this is not by any logic. Usually, what is science? So this is a very fundamental question. What exactly is science? Science is running multiple random experiments, getting a result which matches, and then claiming it and explaining it very logically. But while you reach that, how that particular guy reached that experiment is entirely hit and trial. So this is what science is. Science is everything like hit and trial. If that hit and trial matches up with your assumptions, then you start explaining it logically. But actually, there's no logic. I mean, there's logic, but how did you reach? No logic. Is
experimentation.
Yeah, it's pretty much experimentation.
Yeah, there's a famous quote that says, "Research is what I'm doing when I don't know what I'm doing."
Pretty much. I mean, that's the beauty of science. You do not know what you're doing, but I mean, just random experiments. Then we start explaining the things, and we make logics. And if somebody doesn't understand the logic, we say you don't have a logical understanding. I mean, this is pretty much experimental. A bunch of experiments which became successful, and then those people started explaining the random hit and trials. Pretty much science.
Yeah, it's interesting because artificial intelligence started out very much as something that people really tried to formalize, and it's really shifted over into kind of more of the science mentality of experimentation.
Yeah, I mean, having some industry standard practices is good. Like these are industry-wide practices. Those are different things, but there's usually a lot of experimentation which is there.
Yeah. Okay, well, I guess if you can stop sharing your screen now.
Yeah, sure.
Okay. Okay, well, I'd like to thank everybody for participating. I'm glad we had more questions this time. It's actually very good to do it right after the talk. Next week, we're going to be covering chapter 12, which is generalized linear models. The author actually marked it as an optional chapter in the book, but I think that's for people using it as a textbook. In either case, we're planning on covering it, and that's what we'll be doing next week. And then after that, we'll be jumping into the section that I'm really excited about, which is neural networks, and which actually relates more to deep learning. I feel like all the material we've been covering so far is kind of building up to that. So once again, thank you very much, Antarit. That was a very informative presentation. And are you going to separate your slides, or do you want to just send me the whole thing as a PDF? I mean, I have a link, so I can just save it as a PDF.
Yes.
But okay, I'll just leave it combined, so it'll probably be more logical. Okay. So.
Yeah. I think that would. I think that is up to your discretion. How you. I mean, entirely up to you.
Okay. Thanks. Okay. Well, thanks again, everybody, and we'll see you here next week. Have a good night or a good day, depending on your time zone. Bye-bye now.
Bye-bye.